Hello? Hello? Um, I finally fixed my graphic tablet, and today we are gonna talk about topological sort and Kosaraju's algorithm. I can demonstrate my display now. So, um, topological sort. Okay. In the previous lecture, we discussed DFS, and topological sort is based on this algorithm. Sorry. So, what's topological sort? Topological sort P1, P1, so on Pn is permutation some permutation of graph of verticals of graph G. Which P и PG H P PG H and E less than G for every E in G. So, example. Блин, что с почерком? Example. Так. Example. Ну, okay. We have some graph. We have some graph. For example, так. Okay, например, так. And topological sort of this graph will be 3, 5, 2, now 1, 4. Not interesting example. Okay, you notice that we have H from left to the right only in this sequence, and that's why is topological sort of this graph. So I have a I have to you I have assignment for you. Topological sort exists only for acyclic graphs. Of course, we consider only dialectic acyclic graph in this. I forgot to. We consider not only graphs. We consider dialectic acyclic graph. So how to find top sort in directed acyclic graph? Let me to write some algorithm. Так, сам псевдокод. We consider verticals of this graph and if color of A is white, we just launch the fs from this vertical and what? And we get some. And we get after each iteration, we get black verticals. And these verticals, and we get T out array. If you we get we get in the first we get T out array, and in this array we have the time of when we when we have passed our verticals, and T out in reversed order will be what? Will be top sort. Topological sort. Is it true? We have some h from U to V, and if U V belongs to h, then T out of what? Of U greater than t out out of v. We want to prove it. So we want to prove it, and we just consider two cases. If we work with um, provements of some if we have deal with it with the FS, we consider t out and t it's как сказать, it's usually we consider two cases. Usually it described in two cases. We compare tin u and tin v. So there's two cases when tin u less than tin v, so we enter it to the v later than we enter it to the u. We have some h from u to v, and we enter it to this vertical. We locate it in the statement. So according to this case, and we just use the lemma that we want to prove that this is correct, and we just use the lemma about wide path. By the wide path lemma, V has already visited. V has already visited. Has already been visited. So t out our statement is performs. Okay, we just use wide path lamp. And case B. Tin v less than. Сейчас tin v less than tin u. We consider h when Mm, and in this case, we enter to this vertical earlier than O, and at some moment this vertical will be gray and this vertical will be white, and mm, so uh, this means to if we consider um, just if we consider that t out at t out u less than t out v, it means there's some path, so there exists some path, there is some path from v to u, and that is contradiction with our conditions that we have only we have on acyclic graph. So if at the moment t out v algorithm visited visits u, then graph contains what? Cycle. Cycle. That's a contradiction. It means u white at t out v. So t out t in u greater than, давайте лучше так, t in u greater than t out t in u t out at v. And it less than, and t in u less than t out from u. It's obvious, and we prove, and so we have required statement. So to understand this provement with t in t out, t in is array with time when we enter to the vertical v, and t out is when we go out from the vertical. And all the times is different. Times, by time I mean state, I mean what? By time I mean, как называется-то по-английски? Забыл. Погодите, сейчас посмотрю. One second. By time I mean order of our DFS. In time one, it will be look like this graph. If we have some graph, we have some colors for this graph, and in time and in different time we have different panes of the graph. In time null it look like this. In time one it look like this, and so on. It helps us to recognize what we do when we locate it in our DFS. So the next is topological sort with Kosaraju's algorithm. Before that, we must consider examples. Find how to use topological sort. Так. Find the count of paths in some graph, in non-graph, directed acyclic graph. So let's use DP and let's use topological sort. Let dp is the count of paths in which start which start in V, which answer start on V. Okay, and so the base will be just allocate all the leaves as one, all the leaves of graph as one, or or just all the dp is 1. And the PV and step will be what we consider. We get topological sort of the graph. We have some permutation, and from where there are some edges, and we consider what? And we consider only these verticals. It will be the sum of u jit not u where u belongs to edges, and we just sum the count of paths to all the verticals. That's all. For one thing is that we if we consider some graph and want to find the count of paths to leaves, we don't the dp will be this, and if we consider some other paths in graph, I mean this path that ends in this vertical, we just add 1. So order will be from order will be like in order of reversed permutation, reverse topological sort. If we have topological sort, we just как это написать, и will be pn to 1. Okay. That's very easy, I think. And complexity will be all n plus m, because it's just, so by the way, in topological sort we have all n plus m, because we use just an we just fs. In fs we have all plus n as complexity, and in this example, in this task, we have 2. So Kosaraju algorithm. Next will be Kosaraju's algorithm. I remind you that we consider strongly connected components, and in this task we want to find it. We want to find strong connected components. Of indirected graph. Not only directed acyclic graph, just directed graph. How to what's Kosaraju algorithm implementation? In the first step, we do top sort, topological sort, and if the graph is acyclic, we get some permutation in acyclic. And otherwise we take some permutation. Сейчас так написать. P if G acyclic, else some permutation. Else take some permutation. After that, after we get topological sort, we launch DFS. We launch DFS in the reversed graph. And the reversed graph in order of our permutation. In order after that, after each launching, we get some black verticals, and these verticals will be set of these verticals will be our strong our component. So set of these verticals, set of after each launching we get verticals marked as black, and these verticals and set of these verticals. Will be component. Will be component. No, it's clear to see that topological sort will have complexity O n plus m, and this and this just, and we have in this case on ON plus n complexity 2. So Kosaraju's algorithm is really fast. Example. Let's consider some example. We have we launch the fast and reversed graph. By the way, I don't define what is reverse graph. If you have some edge over in reverse graph, we have reversed edges. So it's clear to see that we have some components. In these components we have between two verticals, each two verticals in components, we have some edge to some pass to some pass between two verticals in both directions, and it's clear to see that if we launch the first, we get some we will get all the verticals that have between them we have pass in both directions. So we get some components, and we have edges, and when we reverse our verticals, we get in topological sort in topological sort we get that all verticals in this have time less than, for example, all the vertical on this component. In topological sort we get we get order, and when we reverse our graph, we start to visiting we start to visiting all of this vertical, and this vertical. This component, and then this component. So yeah, I think I give you some intuition that this algorithm works. So let's have a break for 5 minutes. Let's continue. Так, okay. So we must prove that topological Kosaraju's algorithm works. How to prove it? We have already noticed that if we have some if we have some path in strong connected component, if we have some path from U to V, then we have some path from V to U2, and when we reverse our graph, we get reversed path, and that's why each outer launch of DFS in reverse graph passes only one or more strong connected components. So each iteration, each outer launch of DFS in the reverse graph passes only one or more components. Notice this, and we can reformulate that we must prove that if we have some components C1 and C2, you want to, if we have so we want to prove that T out in V that T out in all verticals in T out C1 less than T out C2. We want to prove it. All the verticals in the graph in C1 have T out less than T out in another graph, another component. So statement. We want to prove statement. Let C1 and C2 are CSS. It's not CSS, SCC. And there at least one there's at least one edge from C1 to C2. it means that then max of what in U belongs to C1 T out C U less than max V belongs to C2 T out V, and want to prove this, so again we consider two cases. This type of kind of provements we consider that mean tin U less than mean tin V belongs to C2. We consider it a normal graph when we do topological sort. We get tin T out. So in this case we have tin let's define it like tin U tin U, and in this case we can use wide path lemma at the moment T out. Что такое? Okay. We can use wide path lemma at the moment T out just T out if we consider in this case we consider TU, TV, and we have that minimum TU less than minimum TV. It means this verticals will be gray sometime in some moment. This vertical will be gray and this vertical will be white. So at the moment T out от V from V C1 is not visited. And C2 is fully visited. C2 is fully passed. Then we get max v belongs to c2, c2, t out from v less than t out of v less than t out u. Okay, we just use white path lemma. In another case, minimum tin v belongs to t2 less than min tin u belongs to c1. Define it, denote it like tin v. So we consider components c1 and c2. In this case, we get the in this we consider the various minimum tin, and notice that there's no path from v. No, again, just like in previous improvement, we get that if we consider that t out max t out u greater than max t out v, we get contradiction. The same idea, the same improvement, почти что, almost. And so notice that there is no edges, no path to c1. Otherwise, we get contradiction c1, c2, c1 tilde c2. Then by the lemma, by the white path lemma, we get that at the moment t out where c1 is not visited. Just like in this previous improvement. Then performs the next contradiction or condition t out v less than T out U. That's all. Do you understand the improvement? Do you have questions? Any questions? Once again, in this kind of improvements, we consider two cases, and according to these cases, we trying to apply white lemma pass white pass lemma, and we carefully look to what happens and prove our theorem. It's time to discuss the FS in undirected graph. In undirected graph. Okay, and so in algorithm we consider that the verticals may be black, white, and gray. When we enter to our vertical, we paint it to gray. So if we have some edge between two verticals, we and we paint it to gray. We do step to the next vertical, and we consider all the paths, all the edges that located from this vertical, and we consider this h2, but we have mark that this vertical is gray. We just don't do the step into gray verticals. Okay, in the FS apply ordinary DFS without with сейчас как это, я забыл слово, сори. With condition in which we check that we there's no in which we check that step make only white verticals. Сейчас по-английски. Okay. Next will be BFS. In the previous lesson we discussed that we compare DFS and BFS work. So BFS will be we can implement DFS like if we consider some edge, some graph. In DFS we want to pass it like to go through this graph like 1 2 5 3 6 4. In BFS 1 2 3 4 1 2 3 4 5 6. So we can implement DFS not only like recursively, we can implement it like in using stack. So we have stack. We put one to this stack. We consider нет. Then we consider children of this stack and put these children to the stack, and so on. In stack implementation is good because we consider, in the previous semester we discussed that recursive implementation, in recursive implementation we have strong ограничения, and but DFS if we implement DFS recursively, we have easier implementation. We get easier implementation. So in BFS, just BFS with DFS. BFS, why we don't consider DFS BFS so detailed? Because DFS is very easy. So Um, in the first implementation, instead of stack, we use queue. Mm, we use queue. We put to this queue for example, we have considered one vertical, and we put 2, 3, 4 to this queue. So we put also children's of in each iteration. We just put all the children's on the vertical. In some order. So of course we layer by layer we consider all the verticals.